Good afternoon, everyone. My name is Carol Werner. I'm the Executive Director of the Environmental and Energy Study Institute. Transmission and how the grid works is a major concern. It is also an area that requires great investment, and indeed the grid is worth billions and billions and billions of dollars. And how we make the grid more reliable, more resilient, how it really works, what are the different roles in terms of federal as opposed to state policy making in terms of thinking about the rules. How do all of these things interplay? We're going to hear about all of that from a very distinguished faculty this afternoon. And in fact, probably by the end of this briefing, and of course we will take questions at the end after you've heard the presentations and kind of the walkthrough of the different components, you will probably feel that you should be receiving continuing education requirements. So we look forward to these presentations this afternoon. I think it's a great opportunity to really have a much better understanding of how this really critical grid transmission system works, and in terms of each component, and as it brings power to our whole economy, wherever we are in terms of our homes, our businesses, how we basically do everything in this economy. It's really critical to have a better understanding so that we can all figure out how to have smarter, sound policy to address it. So I am now pleased to introduce the moderator for this afternoon's briefing, who is Jim Hecker. Jim is the counsel to WIRES. He is at Husch Blackwell. And of course, he is a former chairman of FERC, the Federal Energy Regulatory Commission. So there's nobody better to help lead us through this. Jim?
Well, thank you all for coming. I don't know if there's someone better to lead this, but I have the job. So I think we're going to have a pretty intense little educational experience. You know, why is transmission important? You know, when we started the WIRES group, it was hard to find people who were very interested in the grid or in infrastructure generally. But I'm finding that in policy circles, in industry circles, political circles, talking about infrastructure, America's infrastructure, and how we build a stronger economy, provide jobs, all those things resonate with policymakers. And there's no more important piece of our infrastructure than the electric transmission grid. I should explain to begin with that this is sponsored by WIRES, and you can find a lot of information about transmission on our website, www.wiresgroup.com. And it's a very newsy website, but it also has some important studies and other information on it. WIRES has done, probably we're about a dozen of these briefings on Capitol Hill over the last 3 Congresses, and we're delighted that you found time today to join us. And I want to thank Carol Werner and EESI for helping us organize it. WIRES is a national group of companies, co-ops, municipals, investor-owned utilities, consultants, various people, renewable energy developers, people who are interested in ensuring that we all understand the need for investment in the electric transmission system. It's a system that is critically important. National Geographic did an article on the grid, almost like a force of nature, about a year or 2 ago. And they said we're all embedded in the grid because we depend so heavily on electricity to do almost everything in our daily lives. So electric transmission, the adequacy of that system is essential for our standard of living. That's not an overstatement. That doesn't mean that in the energy sphere, the transmission is the solution to all problems. I think it's important to consider energy efficiency, demand response. I think it's important to look at alternative sources of energy and microgrids. And we have a lot of technology heading at us right now. But we are going to be a networked society, a society that depends on the grid for the foreseeable future. The problem with that is that a lot of the grid is 40 and 50 years old. It's electromechanical. It's starting to be digital. It's congested in many places, which keeps electricity prices high. It is inadequate to connect the rich sources of renewable energy that we find offshore and in the middle of the country. We need to invest in upgrading to digital technologies. And it's vulnerable. Superstorm Sandy was a good demonstration of how we need a more resilient grid. But if you ask the American Society for Civil Engineers how good the electric transmission system is, they give it a D+. They are very afraid that we're going to underinvest in the grid over the next couple of decades. Our economists that we've spent a good deal of time with, project that the country's going to have to spend $300 billion with a B dollars over the next 20 years to accommodate the new technologies, the new fuel mix, the demands for more reliable electricity. And most of that money will not come from government, it will come from private sources. So regulation is extremely important. You're going to hear today, we call it Transmission 101, because we're going to march through a whole bunch of really important issues, starting out with what's a kilowatt. But hang in there, because this information, if you're interested in electricity, is going to be really important, and I think you're going to have this to take home with you. So the faculty, as Carol puts it, is for people who have done things like this before, and the latest being this morning at the Department of Agriculture. And we think that there's a really compelling story to tell about what the grid is, how it operates, who regulates it, and who ensures that it stays reliable even under adverse conditions. Our first presenter is Wayne Galley. Wayne is currently working for Clean Line Energy. He's an engineer, but he's been around a long time. He's worked for NextEra Energy, for the Southwest Power Pool. Clean Line develops high voltage direct current transmission, and you're going to hear the difference between direct current transmission and alternating current transmission from him, as well as a lot of other very basic facts about grid operations. Secondly, Jeff Dennis, who's the director of the Division of Policy Development at FERC within the Energy Innovation Policy Division. And he's a former assistant to Commissioner Norris. Jeff is going to talk a lot about what's happening at the FERC and the implications of what it's doing. Third, Jay Casperry. Jay is Director of Research and Development and Special Studies at the Southwest Power Pool. Jay has a long history in the industry as well, and has been working at SPP, I think, for 10 years or more. Jay has also been a detail to the Department of Energy to help them with their grid tech projects and other transmission planning projects. And last, but perhaps very importantly, is David Cook. Dave is an old friend of mine. He was a lawyer at the FERC. He was Deputy General Counsel there and worked there in various capacities for 20 years. Went on to be General Counsel of the North American Electric Reliability Corporation, which is the designated national, or North American really, reliability standard setting group. I can't think of anyone who understands this business better. We are excited to be here, and we'll try to get through this material and give you all time to ask questions. I think our emails are at the end of the document, so you're more than welcome to pursue us afterwards as well. So we're going to start off with Wayne, and we call him Professor Galley.
Thank you, Jim. For those, just for your information, I am standing, so those in the back can't see me over the podium. I apologize. Got the right button there. Well, again, thanks for coming and taking time out of your schedules to learn a little bit about electric transmission. For some of you, the material I'm going to cover is pretty basic and pedestrian. For others, it might be the first time you've seen it since freshman high school physical science. But we're going to keep it go at a pretty steady pace because I think the goals here are to try to cram into 20 minutes or less an understanding of the complexities of the electric power grid. And the grid is arguably, in my mind, one of the largest, most complex machines that man has ever constructed. From an engineering perspective, it's extremely exciting. As an electrical engineer by training and profession, it's exciting because it's got almost every aspect of electrical engineering involved in it, from electromagnetic fields to circuit analysis to computer controls, to communications, the whole gamut of electrical engineering. And throw on top of that, from an engineering perspective, it's got mechanical engineering, chemical, civil. So it really spans the gamut, and it's a fascinating machine. It doesn't have the sexy allure of nanoelectronics, perhaps, but it's fundamental to our daily lives, as Jim has pointed out, and extremely important. So it's got a lot of neat, geeky engineering aspects to it. But since it's a fundamental element of supplying energy, it also has plenty of meat for policy wonks to sink their teeth into. And we'll find out if you go further, what you start to find out is that a lot of times physics and policy don't often match up, and therein we have some pretty interesting engineering problems to tackle. Sometimes when policymakers don't understand physics and engineers don't understand policy. So hopefully we'll help bridge some of that gap. So in general, basic definitions, voltage and current, you've all heard of these. Voltage you can tend to think of as electrical pressure. In terms of orders of magnitude, just as comparison, your typical household outlet is nominally 120 volts. When we talk about transmission voltages, though, we're talking about 100,000 volts and above, typically. So that's 100 kV, 100 kilovolts. Most of the bulk grid around the United States is 230 kV and up, and you'll see voltages as high as 765 kV. Current is just the movement of charge through a conductor. And then power and energy, often we use those terms interchangeably. From a physics perspective, they're very different. You pay on your electric bill for energy. You don't pay for power. So you pay in terms of kilowatt hours. And typically in utilities, they measure it in terms of megawatt hours, in terms of the amount of power that's used or generated over a period of time. By and large, the bulk of the grid is alternating current, which means that every 60 seconds we go through a full cycle of positive and negative. So the voltage and the current alternate as a function of time. Direct current is akin to the current that you see out of your battery on your car. The batteries that power your cell phones, your computers, all those are direct current based, and you need rectification to get from AC to DC to power those. But we'll see in just a minute that as a function of technological history, that the grid evolved mostly as an AC grid. But there are times when DC makes sense to be used. And so the evolution goes back about a little bit over 100 years ago, what was deemed the War of the Currents. Thomas Edison and George Westinghouse were contemporaries. Edison and Westinghouse, they hated each other, and they fought vehemently for the technology they believed in. Edison was an astute businessman. He had a lot of patents in DC technology, was very politically savvy, pushed for DC being the technology of choice. Westinghouse, on the other hand, understood the benefits of AC, both from a technological convenience of running motors, because you had an alternating electromagnetic field associated with it and the ability to change voltages. It was a very fierce political battle. Edison did things like fund the creation of the electric chair using alternating current to show the evils of alternating current versus direct current. He electrocuted Topsy the elephant. So if you go and you Google Topsy the elephant today, when you get back to your desk, you'll see some disturbing video footage of that from old Edison video footage. So what's a megawatt? A megawatt is a million watts. If you remember Back to the Future, a gigawatt would be a billion watts, right? Megawatts will power 10,000 100 megawatt light bulbs, just to give you a perspective, or powers about 800 average homes, or in hot areas like Houston and Phoenix, about 250 average homes. Our grid is composed of basically four main components. You start with the source, which is the generating station. You go through step up through transformation to the transmission grid. Typically, we think, as I mentioned before, the transmission grid is anything 100 kV and above. Standard voltages will range in the U.S. depending on standards that local utilities have adopted, but typically 138, 230, 345, and 500 kV are standard voltages. Then there's a distribution system that we'll talk about shortly, which is meant to directly serve customers. Larger industrial customers may connect directly to higher voltages, but then household kind of secondary customers that run off 120 volts or 240 volts nominally will be connected to slightly lower voltages. So what this slide does not illustrate, which we'll see shortly, is just the highly interconnected nature of this machine, though. So generation fundamentally is creating the electric energy. Primarily, our fuel source is thermal in nature, so coal and nukes and gas. They basically boil water to make steam. Steam turns a turbine, which generates electricity. And then you have renewable resources such as wind and solar and hydro. Sometimes I jokingly refer to coal as vintage biomass. Loads are the consumers of electrical energy. So a load is your typical house. A load can be as small as your cell phone charger, just a few milliwatts. Thousandths of a watt, up to large industrial customers that are consuming tens of thousands of watt hours or megawatt hours. Distribution portion of the grid typically is radial in nature, which means a line runs out and it has no other interconnections to it. And so if you lose that line, all the load along it is lost. So fundamentally, there's no way to kind of backfeed or loop that system in. So it's typically the type of, when you see wooden poles running down your neighborhood road that are relatively short, have relatively small insulators on them. This is typical distribution. It's not used in interstate commerce and typically not regulated by the federal government. The transmission grid is used to move bulk power over relatively long distances and to reduce losses. And so it also provides for interconnectivity. Jay from the Southwest Power Pool, the history of the Southwest Power Pool is such that it goes back to 1941 in the war effort, when there was not one single utility who could serve the needs of some of the aluminum smelters in southern Arkansas. And so the utilities formed a power pool, and they pooled their generating resources and built transmission to supply the war effort to provide power to these aluminum smelters. So it's just one way to enhance access to markets, access to energy, and enhance reliability for areas of the grid. So without transmission, we're kind of stuck with Edison's model. Edison built the first electric generating plant in southern Manhattan, and it served an area of about 12 blocks and had about 500 customers, and the only load that they had were lamps. They didn't have air conditioning, they didn't have refrigerators, things like that. They had plain incandescent bulbs. So it was a relatively small plant, and you would have to repeat that about every 10 to 12 blocks in order to meet load. So with transmission, though, we can look at energy. Energy typically is something that benefits from economies of scale. So to drive your cost per kW down in a generation facility, it makes sense to make it bigger. 1,000 megawatts of a certain type of technology is typically cheaper on a per kW basis than 500 megawatts of the same technology. So the bigger in scale that you can get, the better off you are in terms of cost of energy. So doing that requires that maybe you are in an area that's more environmentally sensitive or an area that's less environmentally sensitive, an area that's closer to fuel resources, and in order to facilitate that, you need transmission. And then once you kind of have a network previously here that shows kind of the generator networked with the distribution and loads, you can take your network and interconnect it with other networks to help create better markets and redundancy, prevent you from having to overbuild generation capacity. This interconnecting networks is important from a reserve sharing perspective, so that you don't have to overbuild generation capacity to sustain losses in your generation. So again, as I mentioned, it's one of the most complex grids. So this map shows you just kind of what the spider web looks like. This is everything 230 kV and above. So if you put the 138 kV on there, you would probably not see much of the geography. You'd recognize the outline of the U.S. But in terms of bulk transmission, this is kind of just shows you kind of the complexity and the size and the fact that it is highly interconnected. The other thing that electricity is not like other forms of infrastructure like pipes and telecom where information and fuel can be easily routed. It's controlled strictly by the laws of physics. Power flows through the path of least resistance. So once the power is on the grid, you don't have a whole lot of control about where it goes or how it flows. So system planning is extremely important. As I said, it's the grid has evolved primarily as an AC grid as a function of technological history. But there are places and times where high voltage direct current makes a lot of sense. And HVDC is not a new technology. It's been around actually since the 1950s, in this country since the late 60s through early 70s. So anytime you start exceeding a distance of about 300 to 350 miles on a transmission line, it starts to make sense to look at high voltage direct current as the appropriate technology for moving large amounts of power. Cable projects, underground projects also make sense because of the physics of cables and some of the issues associated with burying cable that DC makes more sense than AC does. And then back-to-back ties, we'll talk a little bit about the three interconnections here shortly. And back-to-back ties allows you to connect two asynchronous systems. We'll talk about that just shortly. So this just shows a map of existing HVDC in North America. The majority of these projects were built up through the mid-'80s, with a handful that have been built in the last decade or so. But primarily, they had very specific functions. For instance, the Pacific DC Intertie, which runs from northern Oregon into the LA Basin, was built to move hydropower from Bonneville Power Authority into LA. The Square Butte and the CU line were both built outside of lignite coal mines in North Dakota to move power to Duluth and the Twin Cities. The Quebec-New England line, again, was built to move hydropower from northern Quebec into the New England area. And then you see the series of dots. These are back-to-back ties that I mentioned. We'll see that the grid is actually the North American grid is actually three major distinct interconnections, and those help separate those interconnections. So in general, it's interconnected, so you have to have interconnected operation. Again, this is kind of a cleaner view of the U.S. grid at 345 kV and above, so we've removed the 230 kV. So most of your large bulk transfer is happening on the 345 kV and above. That's where you have the lowest path of resistance in terms of power flow. But that gives you an idea to see how densely it makes sense that along the eastern seaboard and western seaboards, just how dense the transmission is, because you have a lot of load and load growth in those areas. Whereas in the middle of the country, where you don't have a lot of population density, you have less transmission infrastructure. Jay will point out later that you've got a huge, abundant renewable resource, though, in the middle of the country that currently has no way to tap the markets without additional transmission infrastructure. So this talks a little bit about the various interconnections. It's not the greatest colorful picture, but the three primary interconnections that we're concerned with in North America are the Eastern Interconnection, which is roughly the two-thirds of the U.S., the Western Interconnection, and the Great Republic of Texas with the Texas Interconnection. There's a smaller interconnection. Nobody laughed at that. I'm from Texas, I can say that, right? So the Quebec Interconnection, you'll see, is a separate interconnection as well. Within these, so each one of these interconnections acts as a single machine. So the adage, what happens in Vegas stays in Vegas, isn't true in the Western Interconnection. So literally, when a load changes in northern Alabama, from a theoretical perspective, generators all over the Eastern Interconnection actually respond to that. So within the interconnections, we have 8 regions, and these reliability regions. Jay will talk a little bit more about those, Jay and David. But we have these balancing authorities, and the balancing authorities are basically tasked with the job of controlling their generation and their load on a millisecond by millisecond basis. So you see the operator sitting here scratching his head a little bit. The best position you want to see a system operator in is to have his feet on his desk, because it means everything's running smoothly, right? But in all seriousness, a control area is just a metered, electrically metered physical boundary. So we see that on his system, he's interconnected over here on the east, and he's got a meter that defines that interconnection. And he's interconnected over here on the west, again with a metered boundary. So everything within those metered boundaries is his control area. So he's got customers on distribution, he's got generating plants, he's got transmission, all that he has to maintain and operate, primarily with the sole purpose of instantaneously balancing supply and demand. So while we treat electricity as a commodity in energy markets, which it is, it can't be stored. So it's not a corn, or it's not a pork belly or anything like that. It can't be easily stored. It's got to be supplied instantaneously upon demand. So again, that makes this a fascinating engineering problem, as well as a fascinating regulatory and markets problem. So this gives you an idea of the variation in frequency. So the frequency in the US and North America, for the most part, is 60 hertz. That's primarily just kind of a relic of a standard as to why it's 60 hertz and not 50 hertz as it is in other countries. But we settled on 60 hertz in North America, and and so what we see here is how frequency fluctuates as they're trying to balance the load and demand instantaneously. This is actually, I mentioned what happens in Vegas doesn't stay in Vegas. This is a graph of the Eastern Interconnect from frequency from Little Rock, Arkansas during the 2003 blackout. And so what you see is nominally, at that point in time, the frequency was at 59.98 hertz. So it's 0.02 of a hertz below 60 hertz. And part of that's what they call a time error correction. So they were in a time error correction. But you see what happens here shortly after 1230, you see a big dip in the frequency. So that's when some of the generating plants in First Energy started tripping offline. So what happened is your supply went away, but your load was still there. So the system starts to slow down. Well, so the Eastern Interconnect starts to respond and the frequency starts to pick up. Well, then bam, right about 12:55 or so, the Northeast went black. So 50 million customers in the dark, and now you have oversupply, and so the frequency overshoots, and it takes it a while to go back down. So we'll kind of transition now to transactions on the grid and what their impacts mean. So sometimes as a supplier of energy, you might find it more financially beneficial to purchase power from another part of the system because they can generate it more cheaply than you can yourself. So in this example, Utility B is purchasing from Utility A, or Entity B from Entity A, 100 megawatts because Utility A can generate it at half the cost. And so I hire my highest paid attorneys and my best contract negotiators to write up the deal. And they do a really good job, and we schedule the power flow and make the transaction. But what really happens on the grid doesn't look like this. It looks more like this. My power doesn't flow directly from point A to point B. Rather, it takes the path of least resistance. So you look at the sum of the powers going into point B, it's still 100 megawatts, but it didn't go directly from A. It took various routes to get there. So despite my highest paid attorneys and my good contract negotiating skills, I failed to do a direct transfer. And this gives an idea of a very simple transaction that occurred from SPP to the New York ISO, and the number of facilities, critical facilities, that were impacted by 5% or more in that transaction. So you see, this doesn't say that they were overloaded, it just is a fact that they were impacted by 5% or more of that transaction flowing from the Southwest Power Pool to the Northeast. So some of the limitations that you run into, obviously these are physical systems, so they have limitations. One of those is thermal limitations with a line. So a conductor is designed to carry a certain amount of current before it overheats and then turns into molten aluminum on the ground. And so you have to protect that conductor against that kind of activity. Stability issues. Again, you think of the system, if you remember from basic physics, mass spring systems. So when the system gets thumped, if you will, so something happens on the system, a big load switches off, a switching event, a lightning strike, a generator trips off, the system kind of has a thump to it, and it starts to oscillate. So if the system isn't designed properly, it will oscillate and lose synchronism, and so you'll lose more than you anticipated from that system thump. So you have angular stability issues, you have voltage stability issues. All of these are system limitations. And these limitations, last slide, Jim. These limitations result in congestion on the system. And congestion on the system results in uneconomic dispatch. So when markets or utilities dispatch their generation, they always dispatch to the least incremental cost. So you dispatch your cheapest generation followed by your next most expensive until you meet load and losses. But if you have congestion, it forces a redispatch either in the market or in a particular balancing authority. And so now you have an uneconomic solution to provide that balance between supply and demand. And so that's where transmission comes in to help alleviate congestion needs and minimize the risk of congestion on the system. And so with that, you just learned in 20 minutes, 20 years worth of stuff.
Good afternoon. Thanks, everybody, for coming, and thanks for having me, Wires and EESI. My name is Jeff Dennis. I'm at FERC. And what I'm going to try to do here is walk you through sort of the gory details of how the electric power system, and in particular transmission, is regulated. I, of course, have to start with the obligatory disclaimer that anything I say may or may not represent the views of the Federal Energy Regulatory Commission, any of the commissioners, the government, pretty much anyone. So with that out of the way, this slide is just intended to present kind of a high-level overview of not just transmission, but generally how electricity regulation is divided between the federal government, FERC, and the states via state public utility commissions. And what I have here is at a very high level, wholesale sales of electricity and interstate commerce, and transmission of electricity and interstate commerce are both subject to FERC jurisdiction. Contrast that with state regulation, which focuses on the distribution of electricity to retail end users and that distribution system that Wayne talked about. More low voltages and radial in nature, as Wayne talked about. When it comes to siting, there are some differences as well. Siting, by and large, resides with state and local government entities, and we'll talk a little bit more about that in a minute. FERC has a very, very limited role in transmission siting, and it also effectively sites hydroelectric power plants through its permitting process. But otherwise does not do any generation planning or any facility siting. That is strictly with the states and local governments. FERC also regulates the reliability of the transmission system, and David will talk more about that, and I'll just touch on it a little bit. You know, at a high level, I think the most important thing to remember about transmission regulation is that while jurisdiction is primarily with the federal government, it's really a mix of federal, regional, state, and local laws, regulations, organizations that have come together, all with an impact on the transmission grid. And these are just some of the areas where these rules and regulations and practices can impact rate making, what is charged for transmission service. That's kind of the bread and butter of the Federal Energy Regulatory Commission and its work. Operation of the grid, and that's just day-to-day, managing the operation of the grid, deciding, allocating the capacity of that line between various users, those kind of things. Planning, which is an increased focus, subject not only to federal regulation, but also regional organizations organized at the interconnection level and on down that have a role in planning. And then, of course, we talked about siting and also reliability. And what you will note about all of this regulation is that it's got three primary areas of focus. Certainly the ongoing reliability of the system, but also the economic efficiency of delivering energy to end-use consumers. That's the congestion aspect that Wayne talked about at the end. That congestion on the transmission system has a real cost to consumers in terms of that redispatch of energy. If there's transmission on the line, you may have to operate a power plant that's more expensive, that may be subject to stricter environmental regulations, something like that. So there's a real cost there. And also, of course, the ability to create new transmission capacity and add new resources to the grid. And what I like to say when I talk about the transmission grid is to put it in the broader context of the wholesale electricity market. It's really the foundation for competition in wholesale electricity markets, which has been a pretty consistent policy of both Congress and the Federal Energy Regulatory Commission since the 90s. Without that platform, you can't have effective competition between suppliers of power. Another important aspect of the transmission grid is how fragmented the ownership is. There are literally hundreds and hundreds of discrete owners. Roughly 2/3 of those are investor-owned utilities, subject to FERC regulation. Roughly 1/3 are public entities, such as rural electric cooperatives, municipal utilities, federal utilities, such as the Bonneville Power Administration or the Tennessee Valley Authority. And those ownerships obviously affect regulatory jurisdiction. Those other ownership types I talked about are generally not subject to FERC jurisdiction. Another thing that I'll talk about in a minute, but just to touch on here, is that many transmission owners have actually turned over the operational control of those facilities, the day-to-day operations, governing access to those facilities, to independent third parties called regional operators, ISOs, and RTOs, and I'll talk about those in a minute. But that can affect regulatory jurisdiction as well. Jumping to federal regulation, there's actually a number of entities that are involved in either regulation or policy when it comes to the transmission grid. When we talk about FERC, of course, we're talking about regulation of public utilities as that is defined in the Federal Power Act. And essentially what is defined out of that definition is rural electric cooperatives that have rural utility service financing, rural electric cooperatives that deliver 4 million megawatt hours or less in any given year, as well as municipal utilities, any utility that's owned by a state or a political subdivision of a state, and then, of course, the federal utilities as well. And for those of you who like statutes, that's Section 201F of the Federal Power Act. The Department of Energy isn't really in a regulatory role. It's more of a policy and R&D role, collecting data, analyzing policy, and really pushing the envelope on new technologies and things like that. Other the land management agencies, Department of Agriculture, Bureau of Land Management, and those folks have a key role to play in terms of siting of facilities over lands that they hold. And that is an increasingly important issue in the West as renewables are developed. And then, of course, we have the federal utilities I talked about before, like the Bonneville Power Administration and the Tennessee Valley Authority, who operate subject to specific statutes, such as the Northwest Power Act, and generally are not subject to FERC jurisdiction. FERC may have a small role to play in some of their activities, but they're generally not subject to FERC jurisdiction. Diving even deeper now into what the authority of FERC is, FERC has a broad mandate to regulate interstate transmission rates and terms of conditions of service. And so kind of the bread and butter, like I talked about, is rate making, what utilities charge for transmission service, and of course what that ends up in the bill that we all pay. It's been largely, the standard is that those rates have to be just and reasonable and not unduly discriminatory. That's a pretty broad standard. The Commission has spent since 1935 putting some meat on those bones, but it's still subject to a lot of interpretation. But what transmission rates have generally been driven by embedded system costs. What did it cost to build the system? What does it cost to maintain it and operate it? So when you rely on cost of service principles, you rely on those costs, plus a reasonable rate of return on and of investment for the owner of the facility. And in other words, that return on that investment is the profit that the utility makes. And that is kind of the key part of rate making is where do you get that balance right? You want a return that is sufficient to attract investors to that utility, but you don't want it so generous that it's unfair to consumers. And rate making is all about finding that balance. I should say before I leave this slide, cost-based rates are predominant. It's not the only way rates have been set. Recently, the Commission has adopted some policies to allow a more market-based approach through merchant transmission facilities, and it is developing some additional policies to be flexible in that way. When it comes to terms and conditions of transmission service, the overarching principle is open access. The Commission, to give a little bit of history, and to follow up on a little bit of Wayne's history, traditionally the industry was predominantly vertically integrated utilities that owned the generation, the transmission, and the distribution. In 1977, when the Public Utility Regulatory Policies Act was passed, for the first time, we had independent generating companies out there who were not affiliated with a transmission owner selling power. And what they lacked was access to the grid. Fast forward to 1992 and the Energy Policy Act of 1992, Congress gave FERC additional authority to order utilities to quote unquote wheel or deliver power for others where it found it necessary and in the public interest. The Commission used that on a case-by-case basis for several years, and then in 1998 adopted Order Number 888, which was a landmark transmission rulemaking that adopted the principle of open access. And that basic principle is treat others as you would treat yourself. So it requires that utilities provide service to others on the same terms and conditions that they would provide service for their own customers, their own generation assets, et cetera. And the goal is to achieve non-discriminatory access by generation that's looking to get to market. The way the Commission did that principally was adopted a uniform open access transmission tariff that all utilities are required to follow that dictates the terms and service of open access service. Over time, the Commission has added to Order Number 888 through some other landmark rulemakings. Order 890 added the concept of transmission planning as an element of open access transmission service. Order 1000, which I'll talk about a little later, the most recent rulemaking, added to that as well. Other rulemakings have dealt with interconnection service, how generators are interconnected to the grid. That's also an aspect of open access service and has to be provided on a unduly discriminatory basis as well. And just David will talk about this more, but we also adopt and enforce reliability standards that are developed by the North American Electric Reliability Council. And one important note is that FERC's jurisdiction is not so limited in that area. All users, owners, and operators of the bulk power system, including the municipals and the co-ops I talked to, are subject to those standards. Let me talk for a moment about regional operators. Encouraged by Order 888 and other orders, in some regions of the country, utilities have, as I mentioned, given up control of their transmission facilities to independent regional transmission organizations and independent system operators. And they do a number of things. The primary thing that they were intended to do was to facilitate that open access transmission service they were talking about. If you have an independent third party governing transmission service, governing access to the grid, it doesn't have generation or its own customers to favor. And therefore, you can be assured of more non-discriminatory treatment with regards to transmission service. They do a number of other things as well, principally facilitating competition, and in many regions of the country, operating organized wholesale power markets where suppliers of wholesale electricity and related services can compete with one another to serve wholesale needs. These RTOs and ISOs are treated like any other public utility in terms of FERC jurisdiction. The issues that FERC faces in those regions are a little different. It's not just rate making, it's also the market rules that govern their wholesale power markets and other things that come before FERC. And that RTO structure can also affect the jurisdictional status of entities that participate. And it can also create some conflicts with state jurisdiction where things like resource planning, the kinds of generation used, can butt up against some of the wholesale market rules and things like that. And that's a constant balance that FERC is striking with the states. Let me go on to Order 1000, which I think a lot of you have probably heard about. It's the most recent commission action to facilitate further open access to transmission. And there were a number of individual requirements here, but to step back for a minute, following Order 890, which was in 2007, the Commission continued to assess whether there were remaining barriers to cost-effective and efficient investment in new transmission facilities, whether there were remaining barriers to open access by by market participants. And found that there was still a need for reform. There was increased investment in the transmission system coming. Huge numbers were predicted by a number of different entities. The Commission also noted the changing resource mix. Many aging power plants were retiring. States and other policymakers were looking to diversify the mix, add more renewables, and other kinds of resources, and that was really putting new pressures and new demands on the transmission system. That system was designed around the traditional sources of generation and traditional load patterns, and those things were changing. So the Commission adopted new transmission planning requirements, new cost allocation requirements, which I'll talk about in a minute, that were intended at a very high level to ensure that transmission planning remained open and transparent to all stakeholders at the regional level, that transmission planning was better responding to the needs of the system today, and that at the end of the day, transmission plans were produced that reflected more efficient and cost-effective solutions to regional transmission needs than could perhaps be developed at a more local level. And so those regional transmission planning requirements that I note up there essentially require that open and transparent transmission planning processes be put in place by public utilities. How they plan out for the next 10 years, what facilities need to be built, what needs are out in the system. They must have rules on file to make that open and transparent to allow stakeholders to provide input on system needs and potential system solutions. And at the end of the day, what needs to happen is that a plan needs to be developed that reflects the more cost-effective or efficient solutions to regional transmission needs. With regard to planning for public policy requirements, one of the barriers that the Commission recognized was that the planning processes that were in place at the local level based on the requirements of Order 890 didn't always provide a home to plan for things other than reliability needs. We need this to avoid violating a reliability standard to keep the lights on. Or economic needs. We want to plan this transmission line to resolve congestion and lower rates to consumers. But that there was also another category of transmission needs, and that was with regard to public policy requirements. And the best example of that is renewable portfolio standards, where states are requiring their utilities to procure more renewable resources in their mix. In many cases, that was driving the need for new transmission investments. And what the Commission was being told is that there wasn't a home for that in the existing planning processes. And so the Commission required that a home be created for that within the planning processes at both the local and the regional level. There were also adopted new requirements for coordination between regions on a more inter-regional basis to coordinate how they look at transmission facilities that may span their borders and may provide benefits in both regions. The cost allocation requirements were also significant. One of the barriers that the Commission had long addressed and found was that uncertainty about who would share in the costs of a new transmission facility, who would pay, were proving to be a barrier to investment in new transmission facilities. And so what Order 1000 required is that regional planning processes have an upfront cost allocation methodology on file with FERC in a tariff that everyone can see to provide certainty about how the cost of a new transmission facility would be allocated among customers, who would share in the cost of that facility. The Commission adopted flexibility in how the regions came up with those cost allocation methodologies, but established 6 principles to sort of guide that flexibility. And the overarching, the sort of meta principle among all the 6 is that those who benefit from a transmission project must share in its costs, and those who don't benefit from a transmission facility may not be forced to share in those costs. How regions define benefits has been left to regional discretion, and that's something that, that they continue to work through. Another significant area of reform that has proven somewhat controversial has been what I'm labeling the non-incumbent developer reforms. The Commission was receiving many complaints and concerns that new entrants into the transmission system were not able to gain access to the planning process and ultimately be assigned the rights to build a project. And so the Commission adopted various reforms that we can talk about to remove those barriers so that new entrants in the transmission space can compete to build projects. As far as the compliance process goes, the Commission broke the compliance process into 2 phases. Compliance with the regional planning process requirements, and then compliance with the interregional planning requirements. The regional planning compliance filings were all made. The Commission's ruled on all, but just a very small handful. And the interregional filings will actually come in tomorrow unless extensions were granted. I'm going to skip over this for the most part and leave it to you, but there's other FERC authorities as well that come into play here. And the one that I will just mention quickly, though, is that backstop, that very, very limited backstop transmission siting authority that I mentioned earlier. The way that was intended to work was that the Department of Energy, through a congestion study process, would designate national interest electric transmission corridors. And FERC would have the ability to site a transmission line in one of those corridors if a state had not acted to issue a permit within 1 year. A couple of court decisions have kind of limited the utility of that statute. The first being the Fourth Circuit Court of Appeals defined the 1 year requirement not to include the situation where a state affirmatively denies a transmission project a siting permit within 1 year. And the Ninth Circuit also vacated the Department of Energy's 2 designations of national interest electric transmission corridors. So there are no corridors currently in place either. This just provides you a quick overview of where state regulation impacts transmission. And there's 2 things I'll mention here, and then I'll leave you with the slide. The first is that transmission siting, predominantly on the state level, in some states, maybe even many states, there isn't even a statewide transmission siting law. And transmission has to be sited on a county by county or jurisdiction by jurisdiction basis. The other thing I'll mention is that While FERC has primary regulation over transmission rates, in many cases where transmission is bundled to customers along with the generation and the retail distribution aspect, that remains collected through a state transmission rate and is largely under state and not FERC control. So with that, happy to answer any questions at the end. Thanks.
Thank you. I'm Jay Caspary with Southwest Power Pool. Thanks for being here, and I've got some pretty pictures, and I'm going to fly through some slides to talk to you about ISOs, RTOs, markets, and actually how we do grid planning and operations. There's a lot of information on this slide. Before I get into that, I want to ask you a question. How much do you think transmission is as a percent of your total power bill? It's really a really small percent. It's 5 to 10% of your bill. So if you have a $100 power bill a month, the transmission piece is $5 to $10 of that. Transmission is highly leverageable, and like the others have commented, transmission really enables and defines markets. If you don't have transmission, you don't have access to alternative supplies. And supplies is the biggest piece of your power bill. So to the extent you could maybe double the transmission investment from $10 to $20 hypothetically, you might lower your total power bill to $85 or $90 because you're making the energy part of your bill much more competitive. So I just wanted to give you a perspective about transmission. And let's talk about, we've got organized markets in the U.S. And FERC helps regulate those. Really we're trying to not only keep the lights on, make sure the grid's reliable, but we're trying to make it much more efficient. The markets in the U.S. are very unique in that the ISO RTOs that have markets, there's no cookie cutter approach. They're all at different phases of evolution. They all have little different definitions, different terms, different service tariff provisions. So there is no standard market design. But the markets are to help mitigate against like market power abuses, people taking advantage of their position in the market and extracting profits to the extent they should not potentially. So there is an oversight function there. The ISOs and RTOs, those terms are used interchangeably. SPP tried to become an ISO once or twice, and we filed to become an RTO, and we've succeeded the third time around. So those terms are interchangeable to a large extent. Some are single state, some are multiple states. If you look at the Midwest or the Mid-Continent independent system operator, now they go across 16, 17 states in the upper Midwest. SPP goes across 7 or 8 states in the southwest part of the Eastern Interconnection. I'm going to show you some maps. This is the 3 grids in North America. A key thing about Southwest Power Pool, we are unique, sort of like ERCOT, the Electric Reliability Council of Texas, in that we are not just an RTO, a market provider, a transmission planner, the people that actually help operate the grid efficiently, but we're also the regional entity. And Dave will talk about that and what that means under NERC. But these are the NERC regions, okay? And as you've seen pictures, we've got 3 interconnections. SPP actually has control and access to 5 DC ties to the west and 2 DC ties into ERCOT. Okay, so we're kind of the glue that holds together the U.S. grid in North America. And I think that creates tremendous opportunities for Southwest Power Pool down the road. This is a map of the ISO RTOs that exist in North America. You'll notice that the footprint for Southwest Power Pool is actually a little bit bigger than the RE footprint. And that's because the Nebraska entities, Nebraska Public Power District, Omaha Public Power District, Lincoln Electric System, are under the RTO at Southwest Power Pool, but they're not under the RE, the regional entity, which is the compliance and enforcement part of this business to make sure that people are following standards, documenting procedures, and all that. So this is the footprint of the organized markets. You'll notice that there are parts of the grid that have no markets. They basically have bilateral, traditional agreements and arrangements that have been in place for decades. There's been a push to create or force markets, but these are all voluntary. So why is SPP here? One of the key things about SPP is the rich renewable resources we have. If you look at the best wind resources in the continental U.S., they're in the heartland. It looks like the Big 12 football rankings from about 3 or 4 years ago. Texas 1, Kansas 2, Nebraska 3. That doesn't hold anymore because Nebraska's not even in the Big 12, and Kansas sure can't play football right now. But I can say that because I like Kansas a lot. But it's not just wind, okay? In SPP, we have 8,500 megawatts of wind turbines on the ground. We have signed agreements to install 20,000 more megawatts of wind turbines onto our system and onto our wires. That's more than we can handle with the current rules, current market design, the current reliability requirements. But that doesn't mean necessarily that we shouldn't build a grid to enable that so that other people could get the high quality renewables out of SPP. But it's also in the upper Midwest and all around. There's renewables everywhere, just a matter of the quality of them and the quantity of them. But it's not just wind, it's solar. If you look at some of the solar profiles in eastern New Mexico, western Texas, they're very rich resources. Unfortunately, we have very, very little solar development in Southwest Power Pool. We have orders of magnitude more solar farms being built in places like Germany, where the sun doesn't shine, or New Jersey, where it's driven more by local requirements than by the quality of the resources, okay? I just wanted to show you that to give you a feel for why we think transmission is a good thing. As I said before, there is no standard market design. And our job is to be a one-stop shop. If people want to buy power, to move energy within our whole footprint, the 8 states, they come to SPP and we do that, okay? Hopefully in a very efficient way. People don't have to go state to state or provider to provider to daisy chain a transaction like Wayne showed earlier, where the power was actually moved out of ERCOT, across the DC ties into SPP, and then moved into New York. You couldn't have done that transaction before markets, basically. It just wouldn't happen. You'd have to talk to 20 different people to make each piece of that work. So markets really are efficiency, ways to gain efficiencies in markets, and from within the resource commitments and the dispatch of the resources within the footprint to get the cheapest power to the customers throughout the footprint. We talked a lot about transmission and who owns it and who regulates it. I don't want to spend a lot of time on that. Let's go on and talk a little bit about, now clearly FERC regulates us, right? We're in a wholesale market. I think one of the challenges going forward is a lot of the consumers and the markets of the future, the grid of the future, is probably going to transcend all the way down to the distribution system, to the point that that doesn't fit very well with radial distribution systems, where customers may want to install a rooftop PV system, a storage system in their backyard, whatever, in their community, in their neighborhood, their subdivision. That doesn't really fit in the models today for the wholesale system and how it relates to the retail system. The bulk power system doesn't integrate real well with the distribution system. So I think that's going to be one of our challenges going forward. Transmission reliability is the number one, but making the grid efficient is really important too. Tomorrow's transmission reliability project is probably today's economic opportunity, because as you make the grid more connected, it becomes more efficient. Regional planning, I think we've covered that a little bit. FERC requires all of us to do regional planning. I wish I had a graphic to show you that, but I don't. This is kind of the planning process, and it's very transparent. So the regions will look at overall needs. People will come with solutions. We'll vet them. We'll try to find the best solutions and get them out in front of people, make decisions. Now, the ISOs and RTOs do not build transmission. The transmission owners do. So we're not the ones fighting for right-of-ways or permits or siting. We're the ones telling people here's the right solution. So go build it, and we'll get the revenues, we'll allocate the cost in an appropriate and fair manner. Regional transmission planning is expanding. Order 1000 is helping a lot, and I think that it will continue to help us build the grid of the future. In parts of the U.S. that don't have organized markets, there's a lot of bilateral transactions. People make deals. They buy and sell power with their neighbor because it's a joint power plant they own or whatever. They want to do a deal with their neighbor. Now, even in organized markets, people have bilateral transactions. Those are permitted. The organized markets are trying to just make the overall dispatch as economic as possible. It doesn't prohibit bilateral transactions from happening within the organized markets. Hopefully that makes sense. I'm going to wrap this up in a little bit. The key thing about the grid and building the grid is who pays for it, and how do you define the benefits. That's been a real challenge for our industry. What are the right metrics? How do we measure benefits for a transmission project, especially if we agree with the premise that transmission enables and defines markets? Then we need to understand who benefits, because they should pay. Transmission siting is a key challenge. Nobody wants a big ugly transmission line in their backyard, even if they know it'll lower the rates. So that's a real challenge, and that's a local challenge, not a federal challenge. Interregional planning, I think, is kind of on the next frontier. And as we make more and more robust regional plans, then we'll have to work with neighboring regions to see if there are opportunities to do things across the seam between Region A and Region B. And I'm confident we're going to be able to do that. That's it. I look forward to your questions at the end of our panel.
Good afternoon. They cut me to 2 minutes at our deal this morning, so I feel like I'm really in clover here. David Cook from the North American Electric Reliability Corporation. Reliability means different things to different people. To a customer, it might mean the lights come on when I flip the switch, or does a momentary blip ruin a product run? The vast majority of outages occur on the distribution system, and NERC doesn't have anything to do with those. Our focus is on the bulk power system. And for NERC, reliability means that the system is stable, operated within limits, has the ability to deliver the electricity that's requested both in normal times and under reasonably foreseeable contingencies or problems. My colleagues have talked about the benefits of interconnected operation, and they are many, but interconnected operations also carry a risk. Problems arising in one part of the system can have enormous consequences far away. In August 2003, some tree contacts in northern Ohio initiated a cascading outage that within minutes blacked out 50 million customers in 8 states and the province of Ontario. All of the operators are extremely dependent on every other operator doing the right thing for reliability. You've already heard that grid is an enormous, complex machine. In the US, that machine is owned by hundreds and hundreds of people, operated by a lot more. The single machine also spans the US-Canada border. Because it is a single machine, it must operate to a common set of rules, and NERC's reliability standards supply that common rule set. NERC's rules apply to the physical system, and they work regardless of the business choices, the business model, or the various market decisions that participants have made, because they're all dealing with the same physical system. For decades, the rules were voluntary with no enforcement mechanism. That changed in 2005 with passage of the Energy Policy Act and the addition of Section 215 to the Federal Power Act. Now the rules are mandatory and enforceable. In 2006, NERC was certified by FERC as the Electric Reliability Organization under Section 215. NERC develops and enforces reliability standards that apply to more than 1,900 users, owners, and operators of the bulk power system. NERC annually issues seasonal and long-term assessments of the reliability and adequacy of the system. We monitor the bulk power system in near real time. We analyze disturbances and off-normal events for lessons learned. We train and certify industry personnel, and we operate the electricity sector's information sharing and analysis center in coordination with the Department of Energy and the Department of Homeland Security. NERC is a private nonprofit corporation governed by an independent board of directors with enforcement authority delegated from the federal government. The trustees are elected by the NERC members, which include the whole range of stakeholders in the electricity industry. Investor-owned utilities, state and municipal-owned utilities, the federal utilities, power marketing administrations, the rural electric co-ops, independent power producers, large customers, small customers, and government representatives. NERC is subject to oversight in the United States by the Federal Energy Regulatory Commission, and we have comparable arrangements with regulators in Canada. NERC does much of its work through 8 regional entities who have frontline responsibility for the day-to-day monitoring in the compliance program. We also work extensively through stakeholder committees and teams so that NERC can harness the vast technical expertise that exists in the industry to work on the problems. Back to our, oh, that doesn't go. You got a better slide in the print than what this is. Back to our single complex machine. It's designed and operated by humans. Humans sometimes make mistakes. It's a large physical machine and machines break. That happens every day on the system. And so the rules require that the system be planned and operated so that at any point in time we can lose an element in the system, even if it's a very large transmission line or a large coal plant, a large nuclear plant, and the system will remain absolutely stable. Everything is within limits, and the load would continue to be served. And that's what we refer to as the N-1 condition. Things happen like that happen probably while we're speaking. A generator's tripping off someplace, but it doesn't affect anything because of the redundancy built into the system to deal with events like that. One further word about congestion to wrap this up. Congestion on the electricity system is different from other places where congestion occurs. If you're making a phone call and the system is congested, you get a busy signal, your call doesn't go through. If you're on an interstate highway and it's congested, you slow down and you're late getting to your destination. With the electricity system, when it's overloaded, it continues to be overloaded. And so the rules and the operators need to work with limits that they've studied ahead of time to know how much that line can carry. And as that a particular line approaches its maximum limits, they have to start making adjustments in the system so that otherwise the line would literally burn or just simply sag into things underneath. And that's why we place limits on the system, and those limits are what these guys refer to as congestion, but it's what means that we have to dispatch more expensive generation to solve those kinds of problems. Ultimately, it may mean even shedding load to keep the system stable. But it also means that renewable energy may not be able to be transmitted to load centers. It's getting better now, but in West Texas, there was a lot of wind generation that was simply bottled up because there wasn't the transmission to deal with it. So additional transmission is a way to deal with these congestion problems. I'll stop there, and we're interested in your questions. Thanks very much.
Well, you've been drinking from a fire hose for the last hour and a half, and we're happy to field your questions. I think you should have an overwhelming sense right now that this is a very complicated piece of equipment, this electric grid that we all depend on. It's probably the most important thing that you never think about because we are so animated by electric power. It's clear that utilities and RTOs are continually walking the high wire, trying to keep the system up, keep it reliable, that FERC is trying to nurse the industry into the future with various kinds of regulatory initiatives, using its authority, which is not always very extensive, that engineers and other professionals have their work cut out for them, trying to make this infrastructure adequate to serve all our needs, not just today, because when you build a transmission line, it's going to be there for a half a century, but anticipating what the needs are going to be, what the technology is going to be, what the markets are going to look like, and so forth. So just by way of benediction, I hope you understand that this is a very complicated and expensive enterprise, but one that I think we all need to make an effort to understand, as complicated as it is. Questions for this wonderful panel?
Thank you. That's rather loud. First off, could I ask you to expand a bit on why current market design impedes attaching further turbines in areas in which they could particularly be used? And then secondly, could you guys comment a bit on recent, current, and upcoming developments and projects to shield the power grid from natural disasters and the like?
I think initially that's yours, Jeff, but there may be limitations on what you can say.
Yeah. So the first part of your question was just what's preventing some of this renewable energy from getting to consumers. And I wouldn't call it necessarily, so when you say market design, I have to, my FERC head tells me the RTO and ISO like Jay works at and the market rules they have for the day-to-day operation of their wholesale power market. But backing away from that, it's probably not really a market design issue in that way. It's in many measures a transmission capacity issue. And it's not just that the lines that we have today don't have capacity. It's when you look at Jay's map that he put up of the wind resources, if you were to overlay the transmission grid, you're not going to see much transmission in some of those areas that were deep red and purple, which is one of the reasons that planning for those kind of things and planning for public policy requirements in FERC's mind was really, really important. So that those kind of things could start to be planned. In terms of the second part of your question, I probably would defer a little bit to David, but only I would say that FERC does have a proposal out for NERC to develop reliability standards on the risk that geomagnetic disturbances, essentially solar storms, present to the grid. That's an ongoing effort. It's both, FERC has proposed that standards be both operational, meaning how do you operate the grid to mitigate the impacts of such things, and then any other potential steps that could be taken beyond that. And so it's highly detailed, and Dave might be better to dive into some of that.
In terms of the natural disaster kind of thing, the utilities are in discussion with their, largely their state regulators and their state policymakers on investments to be made to strengthen the grid against things like Hurricane Sandy, and a discussion of what the trade-offs of that would be. Jeff has mentioned the rule that we have underway to develop standards for geomagnetic disturbance. There are already operating procedures in place in many of the utilities that deal with this issue. We learned a lot from a 1989 outage in Quebec caused by geomagnetic storm. And a lot of that learning has already been put in place in terms of operating procedures, and we're continuing to move forward on those. Some of it is a technology and knowledge issue that we're just on the front edge of and continuing to learn about, and I think this is something that will evolve.
I'd just like to add a little bit about the lack of transmission. If you look at the plans that are in place and actually the projects that are being built as we speak, they are significant, at least within regions and RTOs and ISOs. SPP has basically a $4 billion asset base. That's our transmission infrastructure that we've inherited over the last 50, 60 years. We've just started building several major projects out in that sparse part of the grid to harvest the wind resources and to make the grid more efficient. We've actually approved $8 billion worth of new transmission projects. So your $5 transmission component of your bill is going to go to $15. But the good news is your total cost will go down from $100 to like $80, okay? But it takes time to build transmission. And the biggest thing you've got to get over is this hurdle of uncertainty regarding cost recovery. And FERC Order 1000 is going to help with that a lot. And how your cost allocation methodology probably will evolve with time. Ours has over the last few years. And right now we have a very simple and fair approach, that if it's basically a highway project, a very high capacity, high voltage line, everybody pays because everybody benefits. And it took a while to get there, okay? I hope this whole industry can get there at some point and we could start building bigger projects across regions. I think that's one of the limitations, is that there isn't projects to move renewables beyond one region right now. Things are being proposed, and hopefully others will get implemented. But the lack of transmission is one of the constraints right now.
Andy Coons with the U.S. High-Speed Rail Association. We're proposing a national high-speed rail system for the entire country, which is about 17,000 miles of all new electric rail. And I'm curious, can the grid handle that now? Or is there enough generating capacity on the ground now with power plants, renewables, and the grid to handle a major new electrical users such as this, and also as we ramp up electric cars? That's my first question. The second one is, if you actually had private investment money, plenty to work with, what would you actually invest it in to get the grid to the ideal state? I'm not sure who to direct that to, but whoever.
Let me start, and others please contribute. You know, on our radar screen, when we look out at 10-year and 20-year forecasts, we do not have infrastructure like electrification of the railways in the forecast. Could we serve it? It kind of depends on where the load centers are and how they are located relative to the existing grid and the planned reinforcements that are in place. I would hope we could work together and make it happen. A lot of people are having forecasts for electric vehicle penetration, especially in San Diego and some other markets, and that is affecting how their distribution system works and how the loads are stressed on the transmission system too. So that is being captured to a certain extent, but probably nothing close to what you're anticipating.
Well, Jay, just a little plug for your company, though, is as you look at some of the regional planning processes, one of the things that SPP is facing now is this shale gas explosion, and all of a sudden load is appearing in the middle of nowhere where they didn't expect it and they didn't plan for it. And so within SPP's planning process, they've instituted this, I'll get the acronym wrong, but it's a high priority planning study, essentially to address kind of this need that has mushroomed overnight. So I think there are mechanisms in place as if an infrastructure like that were on the horizon that would kick in. I know this is happening in SPP. I'm sure the other entities have similar mechanisms that they can kick into play for those kind of things.
One thing to add about that high priority incremental load study, my group's managing it, so it's a challenge, and just trying to get our hands around good data to understand what the forecasts are and that they're consistent and they're believable, and that we can develop robust and least regrets plans that actually will give us some options down the road should loads change, should the economy shift, whatever. We need to focus on that. But that is going to be one of the challenges for us.
I think it's useful to that demand for electricity is increasing at a relatively low pace. But there's a tremendous demand for capital and for new investment because the system is expected to be ubiquitous, reaching places it's never reached before, to be more resilient, and to be more animated by digital technologies. So the question about what would you invest in, even without this very interesting rail scenario, there is a prospect of $200 to $300 billion in investment. And so is there enough on the ground right now? I would venture to say that this is not that if we were to take a snapshot today, it would probably be very problematic. As the generation mix changes and the grid becomes stronger and we become more efficient in our use of energy, we could probably accommodate that kind of demand, but it's not something that we could do today, I don't think. I have a question over here.
Hi, thank you. Oh, I'm sorry. Hi, thank you. Thank you for holding this today. It's been very informative and insightful. I was hoping, and I'm bringing the conversation back a little bit, that you could expand on how does stricter environmental regulations impact the economic efficiency of delivering energy to the consumers, and if you have or if there are any recommendations on how to remediate that issue.
Anyone?
I mean, I would start by, so this has obviously been a huge topic over the last couple of years with new EPA rules. And, you know, one of the things that's mitigated any kind of a rate impact and will continue to is just the low price of natural gas. Natural gas has really helped to bridge this transition. I think planning processes have a role in this too. Planning processes that are nimble, that can take account of retirements of power plants that are pressured by environmental rules, and that can plan solutions, not just, you know, because you can replace a power plant with transmission, you can replace a power plant with another power plant, there are a number of different things you can do, and I think having open and transparent really going to help that situation. What the rate impact will be, I don't think I could say in large measure, because it depends a lot on how utilities choose to address those rules, whether they choose to retrofit, retire, or do something else. But one of the requirements that FERC has for planning processes is that they consider transmission as well as non-transmission alternatives on a comparable basis. And that can help to kind of make those trade-offs between, do I build a transmission line, do I reinforce a substation, whatever I need to do, that can help with that.
Other questions? Yes, sir.
This is also probably building on that same question. I know utilities have been really struggling with the changing way we generate electricity, because solar, you know, the grid that was meant to push power out in one direction, now power has to go the other way from household solar. We have variability in these huge wind resources you're talking about. But how is your life changing on the high voltage end when we talk about electricity moving in two directions and dealing with the variability? What's what is really new in the high voltage transmission grid that you're doing to cope with these new resources?
That's a great question. Let me start. One thing about the variability of renewable resources, whether they're wind farms or solar farms, they actually complement each other. If you look at the patterns, at least the onshore, the wind in the heartland, in the plains, is basically, some people have called it phantom power because it comes up at night and comes down in the morning. The solar is just the opposite. One thing that you'll find is that if you have a robust transmission system, you can really deal with the variability across broad geographic areas to the extent that you could actually mitigate a lot of the problems with a single balancing authority, for example, trying to chase the wind in their backyard. That's one of the reasons we're going to a broader consolidated balancing authority at SPP, where we'll take 16 entities that are all chasing the wind and the resources within and balancing second by second, like mentioned. So we'll go to one aggregate balancing authority. There's huge benefits of that. Bigger is better because we can somebody's wind farm will be ramping up while somebody else's is ramping down. And now we just have to chase the net aggregate ramp, which is probably much more manageable. So market design helps with that, but you got to have transmission to be able to do that. And we're working on that. It's a good question.
Yeah, and to sort of add to that, one of the other things that variability drives, if we were doing Transmission 102, or maybe it's 201, Wayne would probably talk to you a lot about what are called ancillary services, which are all the other things that you need to make the grid operate stable in a stable way. Things like frequency regulation service, which is power that's used to manage frequency. Those needs become greater when you have more variable resources on the system. But one of the things to keep in mind is that there's always been a variable element on the system, and that's load. The difference now is we're also adding generation as a variable resource. And one of the things that's driven, and this is as much a wholesale electricity market issue as it is a transmission issue, is the need for flexible resources that can respond quickly. Traditional coal plants, large nuclear plants, they don't ramp up and down quickly. The oldest coal plants can take 12, 14 hours to start up. And so we're seeing systems with a lot more need for very quick start type resources that can be on the grid in 30 minutes, an hour, even less. So that goes as far as trying to develop storage and things like that that can come on the grid really, really quickly.
One other comment to make in that regard, variability of renewables is being addressed to a large extent by much better forecasting techniques today than we've had in the past. So there's utilities actually hire meteorologists now to understand the wind fronts and what that's going to do to their wind farms, or what that's going to do to the cloud cover, and what it'll do to their solar generation throughout their network. So better forecasting is a high priority, and there's a lot of resources going to that because there's a huge value there. If people can actually schedule and understand how much risk and uncertainty there is next hour or 4 hours out.
Yes, sir.
I've had a question for years now. How viable is direct current for transmission lines as opposed to the alternating current? Can they be buried?
Well, two questions there. So the viability, it's 100% viable, so it's a proven technology. If you look, and I'll just use China as an example, if you look at the Chinese grid right now, they have a very similar situation where the majority of their population lives or lives along the coast. They have huge resources inside China, and so they currently have about 6 HVDC projects that have been built in the last 10 years, and they have probably 1 per year for the next 20 years planned, and they've broken the barriers. They go plus or minus 800 kV, moving 6,500 megawatts. They've just pushed the vendors to break the 1,100 kV level on it. So It's been proven in this country, so it's a very viable technology for the right applications. If you look in Europe, they're proposing networked DC because of its efficiencies. Burying DC or AC for that matter is obviously something that is on everybody's mind, and there are applications where burying lines make sense. There have been a couple of projects proposed in the PJM, for instance, that utilized existing right-of-way to enhance existing capacity using buried cables. The technology is such right now that at about 1,000 megawatts is about the limitation. Cable systems, it's not as easy as just burying it. There's a lot of physics and heat transfer stuff that goes into that. So it's when you think about a cable project, it's actually a cable system, because if you think about over short distance, the atmosphere surrounding that cable, for instance, if it's a subsea cable, is very conducive to cooling it and keeping it cool. So you keep the cable size relatively small, you keep the insulation requirements relatively small, that kind of thing. Once you go to large power and long distances, overhead is pretty much the most efficient way to do that. Because if you start trying to bury large cables over topologies and geologies that are varying quite a bit, it becomes a very complex system. And then it's not a matter of if you have an outage, but when you have an outage. Those outages are typically very extended in nature, because you have to locate the fault, then you have to excavate it, and splicing large cables is a very time-consuming effort, whereas outages on overhead transmission can usually be repaired in a matter of hours, if not days, depending on the extent of the outage. So there are some projects where it makes sense to bury the cable. There's others where it's beyond the envelope of the technology we have.
I just want to ask a follow-up question. You mentioned China. They're currently building something like 10,000 miles of brand new high-speed rail, and it's coming online really rapidly. Are they having to expand their grid really rapidly to meet that? Because they're also building metro systems that are electrically powered, and so they must be quadrupling their electrical demand almost overnight. How are they doing?
I don't have the statistics off the top of my head, but you know, China is responding. They're responding in their grid growth to just their industrial growth and load growth in general. So they've got massive transmission expansion plans and energy expansion plans. It's easy when you have one regulator and one landowner in the country sometimes to cite these projects, though. So the regulatory paradigm is a little bit different there as well. So.
Yeah, the Chinese arguably have the biggest grid in the world now. But you know, central planning is not something we do. And boy, I can tell you, you know, if we had to, well, let's put it this way: if the interstate highway system would have been regulated like the electric transmission system, I don't think we would have built it. We'd still be on two-lane roads. Let me make one brief commercial announcement, and I'll turn it back to Carol, who will probably give us a benediction of some sort. But we've talked a lot this afternoon about the benefits of transmission, and even in the industry, it's not always completely understood how particular projects provide benefits, particularly over time, because they are such long-lived assets. The WIRES organization is going to publish a study in about 10 days that addresses this all in one document for the first time, and kind of outlines the experience the industry has had in the last decade with planning transmission according to what the long-term benefits are going to be. You can build a project to access renewable energy. The Sunrise Power Link in Southern California is a good example. And then the local utility decides to cancel operation of its nuclear plant. Suddenly that project now becomes a big insurance policy, a big reliability project. And that's the strength of having a grid, an integrated grid, is that transmission serves multiple purposes at different times. It also means that it's very difficult sometimes to persuade people that transmission is needed because they don't see the need as being immediate and obvious. Check our website in about 10 days or 2 weeks and you'll have access to that document. I think it'll be pretty interesting. Carol?
Thanks, Jim. I just want to thank everyone for being here. I want to thank you, Jim, and all of you guys in terms of this wonderful panel. It would be good if we could now think about doing another like 201 or whatever, because I think that there are so many questions, other areas as we look at the whole role of electricity in our very complex and interconnected economy. And so we would welcome your feedback and questions to any of our panel members as well as to EESI. The presentations will be up on our website, and so that you can actually see in better color and larger than on your handouts. So please take a look at that, and the video from today's briefing will also be up there. So I want to say thank you all for coming, and thank you very, very much to our wonderful panel.